Hi, welcome back to General Chemistry 1. I'm Dr. Fang Xu, and today we're going to talk about quantum numbers. And this is the last video of Chapter 7. So, before we talk about quantum numbers, let's briefly mention what a Schrodinger's equation is. A simplified Schrodinger equation, or an easier format of a Schrodinger equation, is H psi equals to E psi. So H is a Hamiltonian operator. You don't know exactly what that is. You just need to know it's a symbol in the mathematical calculations. Okay, so Hamiltonian times psi, which is Greek number, and that refers to a wave function or an atomic orbital. Okay, includes all the information of atomic orbital. So Hamiltonian times psi equals to energy times psi. And if we know the meaning of the psi itself, it describes the motion of electrons. But if we do the psi square, refers to the probability of finding the electron in a location. Okay, so electron densities, in other words. Don't ask me why. That's beyond the scope of General Chemistry 1. Okay, so if you know the meaning of psi square, then we can design or create better ways to describe what exactly electrons are there in an orbital, okay, or the location of electrons near an atom. So we call that probable location of the electron. In this video, we actually do a better modification of the previous model, which is the Bose model. That means electrons are sitting in the circular orbitals. Actually, later on, what people find out is that, no, these electrons does not sit in just the one circular orbitals. It has different, it can show up almost everywhere around the nucleus, but the probability are different. So instead of drawing a circular map, we can draw a probability map. Everything is about probability. So usually we can draw the atoms here. Just take hydrogen, for example. So the nucleus is in the center, as you can see in the panel A. And around the nucleus, there are many dots. So A is actually the electron density diagram or electron cloud depictions. Electron cloud is a more advanced model to describe an electron than the Bose model or the orbital model. Okay, so each dot or the density of these dots represents the probability of the electron being within a certain volume. If you see there are more density of the dots near the nucleus, that means there is a higher probability for electron to be found near the nuclear area. Okay, so if we draw the probability density phi square over the distance of distance to the nucleus, you can see the diagram in panel B. Okay, if you have if the electron is getting super close to the nucleus, then the probability to find an electron there is super high, right? Super high, super high. And then if you're so far away from nucleus, the probability drops, but it never drops to zero. Well, you know, you won't, we never want to say, well, for sure there's no electron there. It could be an electron, thousands of meters away from this nucleus. It's just the possibility of that to be happen is very small. So in this diagram, we never say this probability reaches zero. Okay. And this is the concept of statistics and the probability. All right. So if we move to the panel C, the central one, so you can see it's similar to the electron density diagram, but we have this rings, right? Rings around the center. So this is actually the total probability density at some distance from the nucleus. These rings you see is actually means each layers, and the corresponding diagram you see in panel D is the counting the dots between the neighboring of the layers, between the neighboring of these rings. So that can give you the total probability of electron being in that layer, being in this layer between the rings. So if you say each ring, if you cut this rings into, if you create a lot of very dense rings around the center, you can actually calculate many data points and plot those in the panel D. So when the electron is really close to the nucleus, we know the electron can never go into the nucleus, right? So when the distance r to the nucleus equals to 0, that means we are at nucleus. There's no way we can find an electron there. So the probability is 0 for electrons to show up there. Then the probability of electrons to be found close to the nucleus goes high, right? So from 0, there's a sharp jump to the very high probability. Then, like we see in the panel B, it decreased over the distance of nuclei. So these two, both of these two can describe better than the Bose model of how the hydrogen atom looks like and how electrons show up around the hydrogen atoms. But how are we going to define the size of an atom? As we see here, even it's very far away, electron is very far away from the nucleus, there's still a small possibility that electrons can show up there, right? So in order to make a fair comparison, and we don't want to make too much error in defining the size of electrons, we usually use a 90% probability contour to represent the size of the atom. So here you can see it's like just a sphere ball in XYZ direction. So in the center of this origin of this coordinator, XYZ coordinator, this is the nucleus, where the nucleus is. Okay, so then you may ask, where is the energy level 1, 2, 3, 4? We discussed it before. How are we going to understand that with this electron density diagram? We're going to talk about that later. So, and in order to do that, the electron density is, you can see that as a convolution of all electron orbitals together. Okay, we need to find some method to look at each electron orbitals in this electron density diagram. And in order to do that, we have different quantum numbers and quantum numbers for an atomic orbital. So you can also see this in your textbook, table 7.2. Okay, we have in the 7.2, they list the 3 different quantum numbers. Well, every time we say quantum numbers, we know it's an integer starting from, no, it can be an integer, it's 1, 2, 3, 4, or 0, or negative 1, 2, 3, 4, right? So we have the principal quantum number, which has a symbol of n. Okay, that's the one we are most familiar with. That's define the energy of that level, like that orbital is, right? So it defines the energy and also defines the size of the orbital. We're going to talk about that later in later slides. And for n, for these quantum numbers in the quantum theory, it cannot be any values. Okay, we have to define the region of this number. For principal number n, it has to be a positive integer. So which means it can only be 1, 2, 3, 4, 5, 6, 7, 8, etc. It cannot be negative, cannot be 0. It has to start with 1. All right. So besides the principal quantum number, we also have the angular momentum, which with the symbol of L, lowercase l. Okay. For L, we need to know the rule. So the L has to be from 0 to n minus 1. So if n equals to 1, then L can be 0 to 1 minus 1, that equals to 0. So n can only be 0. If n equals to 2, then L can be 0 and 1. If n equals to 3, then L can be 0, 1, and 2. Always 1 less than the principal quantum number. Okay. And we define the allowed value for L. And usually when we talk about L, it has nicknames, okay? Not just 0, 1, or 2. We have the corresponding name for different L, we also call that subshell's name. So when L equals to 1, we can also call it an s orbital. When L equals to, when L equals to 0, we can call that an s orbital. When L equals to 1, it's a p orbital. When L equals to 2, it's a d orbital. And when L equals to 3, it's an f. 4 is g, 5 is h, when 6, so A, B, C, E, F, G, H, I, right? So then so on and so forth. So that's what an L is. You need to know the rules, allowed values, and its corresponding nickname. Besides angular momentum L, we also have the magnetic quantum number m sub L. Okay, for m sub L, the allowed value is this negative L to 0 to positive L, still integer. So for when L equals to 0, ml is 0. When L equals to 1, it can be -1, 0, +1. When L equals to 2, the magnetic quantum number can be -2, -1, 0, +1, +2. So on the right of this table 7.2, it lists all the possible quantum numbers with principal quantum number 1, 2, and 3. So it's like a tree. Yeah. So there's another quantum number it does not mention in table 7.2, and I think it's worth mentioning here. That's the spin of an electron. That's also a quantum number called m sub s, the spin. Okay, and that can only have two numbers, +½ or -½, and that corresponding to that for each smallest orbital, you can only hold two different electrons, one spin up, one spin down. So which means for each ml, it can either be +½ or -½. And for this spin of the electron, it's not an integer, it's different from the rest. All right. So for this chapter, we require students to be able to know the rules of these quantum numbers and be able to identify what is wrong and what is right and what is wrong quantum number with a given set. All right, so let's go through a few practices. What are the possible L and m sub L values for n equals to 4? You may bring out the spreadsheet and list all of the values by yourself. Since it asks all the possible values, so we can list them out one by one. When n equals to 4, first that can define the range of the L, right? So L is from 0 to n minus 1. So in this case, L can be 0, 1, 2, and 3, right? The n minus 1, 4 minus 1 equals to 3. And for each L, we can have a set of mLs. So mL is -L to +L. And for when L equals to 0, mL equals to 0. When L equals to 1, mL is -1, 1, 0, +1, +1. When L equals to 2, mL is -2, -1, 0, +1, +2. When L equals to 3, then m sub L is -3, or -3, -2, -1, 0, +1, +2, +3. So just list all of them. Let's take a look at another question. What is wrong with each quantum number designation and or sublevel names? So we have a list of n, L, m sub L, and name. So for A is 5, 3, 4, 5F. B is 2, 2, 1, 2D. C is 6, 1, -1, 6S. So you need to identify what is wrong here. Okay, let's take a look at it together. I usually do from the left to the right. So assume n is right. So 5 equals to n, that's good and that's fine. N is 1, 2, 3, 4. As long as it's integer larger than 1 is good. L is from -1. So L is from 0 to n minus 1. So L can be from 0 to 4, which is also good. And L is -L to +L. So it can be -3 to 3. Now it gives you 4. So that's not good. That's wrong. For the name of the subshell, when we're counting L, we're counting from 0, right? 0 to 3, so it's a fourth one. And then when we count the sublayer, so it's SPDF, so it's 5F, that's correct. 5 corresponding to the main, the principal quantum number. So for A, only M sub L is wrong. For B, when we have N equals 2, that's good. And L can be 0 to n minus 1, so it can be 0 to 1. Now we have 2, so that is wrong. NL can be -L to +L, so the largest number ML can be is -1 to +1, so that's good. That can be true. And for the name, 2 corresponding to the principal number, that's good. D corresponding to SPD, so that's the third sublayer, and it's 0, 1, 2 that corresponding to L equals to 2. Well, if we think this L equals 2, that's correct, then this name is correct. However, L cannot be 2, so the sublayer cannot be 2D. Let's look at the last set. When n equals to 2, L is 0 to n minus 1, so it can be 0 to 5, so that's good. And then NL can be -1 to -L to +L, so that's -1 is also good. For the name, well, it's 6 that corresponding to the N, but when L equals to 1, the corresponding name is P, okay? When we count that, L start to count from 0, not 1, so it's 6P. That's wrong. Finally, what are the quantum numbers for the 4F orbital? Okay, for this 4F orbital, we have very limited information. So 4 is the principal quantum number that n equals to 4. And F is the name of the subshell that corresponding to L. So SPDF, F is the fourth one. So it's 0, 1 to 3, L equals to 3. So, but for M sub L, we don't have further information. And if we want to name that, is the 4F, X or Y or whatever. So those parts we don't require here. All right. We talk about these quantum numbers, right? So what are exactly these quantum numbers control over the shape, over the electron orbitals? So let's take a look at that. You may be familiar with solar system. So we have a sun in the center, different planet sits in the orbitals around this central sun. This is also similar to the Bose model, right? So we still can use some of the concept here, that is electron in an atom sits in orbitals, okay? However, the orbital we talk about in electrons is different from the circular orbital you see here in solar system or in the Bose model. For total amount of orbitals, that number is set, okay? And it's defined by quantum numbers NL and NL. It's not continuous and we can jump between different levels. So that's the same thing here. And each orbital can accommodate up to 2 electrons, not just 1. So it can be 2 electrons, one spinning up, one pointing down, spin up and spin down. And for each orbital name, we usually use N, the principal quantum number, plus the subshell's name, SPDF. And also it's optional, but you can also include the subscript of M sub L. So altogether, we can use a symbol to refer to an orbital's name. For example, 2px That 2 refers to the quantum number 2, p refers to the subshell p orbital, or L equals to 1, x refers to, the n sub L, the magnetic quantum number. Okay, so let's take a look at exactly the more accurate model, how to understand the n, L, and m sub L in hydrogen or other atoms. So one concept I want to make it clear is for an atom, it always have these orbitals. It's just some of the orbital is occupied by electrons, some of the orbitals are not occupied by electrons, but orbitals are always there. So let's visualize the quantum number, principal quantum number n. We know n can start from 1, 2, and 3. So here gives you only half of the shape, so allow you to see through, but n is kind of a sphere, more or less sphere shape of n equals to 1, n equals to 2 in the middle, and n equals to 3 here on the right. So all of the n's give you more or less, sphere shape, and that it's a principal quantum number can define the size. As you can see, when n increases, this ball gets bigger, can define the size and the energy from the Bose model. So although Bose model does not give us a very accurate understanding of how electrons circulate, how electrons move around the nucleus, it gives us more or less good predictions on the energy levels. So we can still use that equation for calculation. Okay, so it gives the energy level of a share of electrons. So as we see the Bose equation here. If you are curious of this, the size and energy of this n, so if you see these details, when n increases, there are different nodes, okay? And there are many orbitals in the n. It's actually a sum of all orbitals in that principal quantum number in this size, okay? So, and all orbitals within the n together will occupy approximately as a sphere, as you see here, which corresponding to the size and energy of a shell of electrons. So when n equals to 1, we call it a shell, n equals 2 is another shell. We have different shells. And within shell, there are subshells, then that's where L plays a role. If you take a close look at this schematic, in the bottom, you will see, if you see from the center, the radial probability of distribution from the center of the atom to the outside of the atom, you can see here, there are a few points that actually reaches 0. When we have this probability of finding electron drops to 0, we call that there is a nod. Okay, and this concept will be talked about later. Okay, so now we just try to introduce that here. So now you know what n defines the size and energy of a shell, and that shell is combined, it's made up by multiple orbitals here. Then we can look at or visualize the quantum number L, angular momentum. We already said when L equals to 0, L can be allowed to have from 0 to n minus 1, right? So when n equals to 1, L can only be 0. So for principal quantum number equals to 1, we only have one s orbital, right? So s orbital all looks similar. So s orbital looks like a sphere. Okay, all electrons can actually move inside of the sphere, not just on the periphery of the sphere. It can move inside of the sphere. Okay, every part inside. And then when we move to higher principal quantum numbers, L can allow to have 1, 2, and 3. Let me just give a few examples. When L equals to 1, we call it p orbital. So here's an example of p orbital. It's like an, long, a narrow or a slim 8. Okay, so when you have this p orbital, it does not mean that electron can only travel outside. It means electrons can go inside. It's just the probability to show up inside of this 2 lobes are way more higher than outside. Okay, So this is the shape of p orbital. Looks like this. And then when we have d orbital, that means L equals to 2, we have 4 different lobes in different orientations. Sorry, 4 different lobes occupying the space. So sometimes when we have another shape of d orbital that is look like a p, but you have a ring in the center. So these are also d orbitals. We have different types of d orbitals. So for L, you can tell now the angular momentum L controls the shape of an orbital. It can be sphere, it can look like 8, number 8. It can be 4 petals, 4 lobes occupying space, or it can be a look like p orbital but has a ring in the center, or have more complicated structures I did not include here. All right, finally, let's see what does the magnetic quantum number m sub L defines. M sub L is defined under the umbrella of L, under the angular momentum. So when we have an angular momentum, for example, p orbitals, it show up in this lobe, right? Like an 8 in the space. However, it can show up in multiple directions. It can point along this z direction, it can point along the y direction, can point along x direction. So for p orbital, when L equals to 1, NL can be -1, 0, +1, right? So that corresponding to 3 different orientations, along the x, along the y, along the z. So if you draw schematic converting or including all p orbitals together, you will see here, okay? You have 3 different p orbitals joining together to form, all the possible orbitals under L. L equals to 1. Okay, so when L equals to 2, as you know, we have 5 different M sub Ls. So there are actually 5 different orientations. It can, we have this 4 lobe. It can be the YZ plane. It can be in the XZ plane. It can be in the XY plane, or it can along the X, along the Y, or it can have this shape along the Z square. So you can see when you notify that it's 3D YZ, 3D XZ, 3D XY, 3D X square minus Y square, and 3D Z square. So this subscript of Y, Z, X, Y, so on and so forth, corresponding to the M sub L, and that corresponding to the different orientation of an electron orbital. So again, you can merge all these 5 different orbitals together. So you can see on the right, it's very crowded, but that's the 5 3D orbitals showing up in one schematic here. Almost look like a sphere, I would say. Yeah, so the magnetic quantum number M sub L controls the orientation of an orbital. All right, this is the end of this video, and I'll see you next time. Bye.